Hello, my dear student. I'm Mr. Kitwala from Educators. I will be with you in physics for Form 5. So, welcome again for our topic of rotation of a rigid body. For our subtopic of the moment of inertia as we observe here. But before we proceed with our discussion here, we are supposed to remember where we ended on the last session. On the last session, we tried to see how can we obtain the moment of inertia for a solid sphere. And we said that the moment of inertia for a solid sphere must be obtained by taking 2 divided by 5, then we multiply it by mr square, where m represents the mass of the solid sphere, while r represents the radius or the distance of the solid sphere. That is what we tried to demonstrate on the last session. And after there, we tried to see the relationship, the variation of the percentage between the moment of inertia and also the mass of the solid sphere. And we said that all of this because they vary. When the moment of inertia increases, even also the mass of the solid sphere increases. That is why we try to look at when the mass of the solid sphere, the percentage of the solid sphere increases by 1. Now also that moment of inertia, the percentage of the moment of inertia should be increased by 1%. That is what we try to demonstrate on the last session. Now, for this session, we are going to see how can we demonstrate, how can we derive the moment of inertia for the whole sphere. And I told you that the sphere is categorized into 2 parts. Now we have the solid sphere. For instance, this is like the ball bearing we try to see on the past session. But the second, this is over for this solid sphere. We try to demonstrate its formula. Now after there, we tried to look for. We are going to look for the whole sphere, like the football. Now we have the football. This give us a nice example of the whole sphere. So, my dear student, how can we demonstrate the moment of inertia for the whole thin sphere? What can we demonstrate the formula of the moment of inertia for the whole thin sphere? As we look here, we have been given, we are supposed to consider the figure. We're supposed to consider the whole sphere. Now, below here, at the next slide, we are going to see the figure that represents the whole thin sphere. And this whole thin sphere containing the mass m and also having the mass, having the radius r. And it is trying to rotate about an axis perpendicular to PQ, as we are going to see through at the center. When it is rotating, my dear student, when it is rotating, try to give how the moment of inertia can be obtained. That is what we are going to see. Now consider an elemental ring. So inside the whole sphere, we have the elemental ring of the radius a and also the small mass dm. Now inside the whole sphere, we are going to see the elemental disk. Now we are going to see the elemental ring or elemental ring of the radius. Ko inside tunaenda kuangalia elemental ring of the radius a and also the mass dm. It means it contains the mass of dm with the thickness of dy at a distance y from the center of the solid sphere. That is what we are going to see on our figure number 9 for our first topic. So as we observe our figure, which represented the whole sphere or with rotation and axis at its center. Now this is the whole sphere. And our whole sphere, my dear students, here, containing the elemental ring. Inside the whole sphere, we have this elemental ring, and this elemental ring containing the radius a, as we see that from the axis of rotation up to the ends, it means to the circumference. Now the radius is represented by a, as we observe here. But my dear student, here, as we see that the distance from the center of the holosphere up to the center of the elemental ring must be represented by dy. But here the elemental ring try to give us the small change of y. It means the displacement or the distance. It having a small change of y. And also this elemental ring contain the small change of mass. Kwa kwenye hii elemental ring, there's the small change of y and also the small change of mass, as we try to observe here. So the distance or the radius from the center to the circumference here must be equals to r. It means radius yetu ni sawa na r ya kutoka kwenye center mpaka kwenye ends of the elemental sphere, as we observe. So after this one, my dear students, now if we take this dotted line up to the center, this which represent right, now we are going to see how can we form now we are going to see how can we form this triangle that are found inside the hollow sphere. So my dear student, here as we observe that my dear students, if we demonstrate here, we should obtain that the distance from the center up to the sphere here must be equals to r cos theta. It means kwamba kutoka hapa kwenye hii center up to this dotted line, baada ya kudissolve. Now we are going to see how can we dissolve first, kwamba kwa nini amepata r cos theta, kwa nini ameweza kupata r cos theta, because this elemental ring containing the small change of the angular displacement, and also the small change of the mass, and also the small change of the displacement. Now we can say that if we dissolve here by considering the Sotoka here, we should obtain, because the distance from the center up to there equals to r. Now if we dissolve, this is adjacent. The relationship between adjacent and also the hypotenuse, which is equal to r, must be the cosine theta. Now cosine theta must be equals to adjacent, then we divide by r. But remember that we are going to see how can we obtain the adjacent. If we cross multiplication, we should obtain that the adjacent must be equals to r cos theta. That is why here I try to write instead of writing adjacent, I try to write equals to r cosine theta. Now this hollow sphere trying to rotate perpendicular on an axis Q, as we see it rotates clockwise moment, as we say we observe the direction of this angular velocity here. Now after this one, my dear student, what we are supposed to do from our figure here. Now from our figure, then from equation number 4.24, now let us recall our equation number 24 for our first topic. The moment of inertia di of the ring is given by this one. Kwa yule moment of inertia tutalikoa ile equation yetu number 24, and we should obtain that the moment of inertia for a ring must be equals to dm times the a square, where dm represent the small change of the mass. This represent the small change of the mass, and a represent the distance of the elemental ring, where di, this is the moment of inertia for elemental ring, as we tried to observe. So since dm is the fraction of the total mass m of the ring, then the mass and the area for the both sphere and the ring can be expressed at this one. Now we are going to see how this how this total fraction can be related by the surface area. Now we should say that because dm is the fraction of the total mass and total mass m of the ring, then the mass and the area of both sphere and the ring can be expressed as this one, my dear students.